how much is your V1? So it's basically you have a DC plus AC as V1. So it is like 1 volt plus 10 millivolts is your combined VAC plus VDC minus 0.6 volt, for example. So assuming that 10 millivolt is much less than 1000 millivolts, so we just say it is 1 volt minus 0.6 volts. So approximately you have 0.4 volt across the capacitor. Therefore, C equal to Q over V. So the charge that you get is C times V on the capacitor, which is equal to 1 microfarad into 0.4 volt. And that is your charge in coulombs. Okay, so just find out how much that charge goes. 1 into 10 to the power minus 6 multiplied by 0.4. Okay, that will be your charge. Now, usually you place a switch across the capacitor actually to reset the charge on the capacitance. Actually, you close the switch to discharge it so that it can start reaching out or monitoring the peak value of the input voltage. So you see, this is basically a half wave rectifier circuit, half wave rectifier circuit, because we have a AC input and we are getting the DC at the end of a diode cathode. But you also see the capacitor is used there as a filtering capacitor, or it is also, the circuit is also working as a peak detector. Okay, this is going to work as a peak detector. Half wave rectifier with a filter capacitor or a peak detector. So let us see the behavior of this diode. So remember, diode PN junction diode has the exponential relationship between the I and VD, and here somewhere we say this is a bias point or Q point of the diode, that is a p-n junction diode, and the current is related to the voltage by this equation, that is Shockley diode model, is e to the power Vd divided by eta Vt minus 1. Okay, so we've seen that before. So let us now see the behavior of this diode. One, we will do the forward biasing, and then the next we will do the reverse. We will just change the polarity of the diode and rerun the simulations again. And we'll see in the current position like this, the diode, the circuit works as a positive peak detector. And when we switch the position of the diode, reverse the direction, where the circuit will behave as a negative peak detector. So what I am going to do, I am going to run the analysis, click simulate, edit simulation command, and I want the DC operating point first. Anything I run, before that I want to see how my circuit is biased and proper operating point. So click OK, place .op somewhere here, press, and then I will say run. And let us see, the voltage at node 001 is this net actually. That's a 1 volt what I have applied. Then output voltage is 0.9999. So obviously my circuit is not working as expected because I'm getting the diode is not into the conduction. Okay. Look at the current through the diode. It is a very small leakage current that is flowing through the PN junction because it is not on. So I have to modify the biasing condition of this circuit. So let me find it out. So how to do that? Right. So we can't really have the DC operating point of the circuit because for the DC voltage at the anode of the diode, the capacitor will act as an open circuit. So with this open, your output is essentially equal to input because diode is not into the conduction. And now what I have done is right clicking the sinusoidal. So I have set the DC offset of 1 volt. I can set it to be 0 also, for example. And then the amplitude of the peak sinusoidal or time varying waveform is set to be 1 volt or 1000 millivolts. So let's say 1 volt, frequency is 1 kilohertz. So what I'm having is from the DC level of 0, my signal is going 1 volt up and 1 volt down at a frequency of 1 kilohertz. So with that now, here, the V1 minus VD would be 1 volt minus VD is 0.6 volts. So obviously 0.4 volt is the output voltage expected. So we'll see how the circuit works. So I am now running the transient analysis. I see that on the top of this screen, I have put this spice command .tran running the analysis for 10 milliseconds. So right clicking it is giving me the syntax. So I have just used the stop time of 10 milliseconds and let the other parameters to be chosen by the circuit simulator itself. With that, I am going to click the run here. And here I have this graph. So before I show you the waveforms, let's clear all the drawing. We are all set. So first, come back to schematic and see the red probe. I click enter. It's now a pure applied sinusoidal wave with the DC voltage level is 0 volt. And then on top of it goes 1 volt up and 1 volt down. With that, now I am going to plot the output voltage, which you can see now, the blue line, and it is about 0 until I have this level. For example, you see here, there is this so you closely observe that up to certain voltage, about 0.6 volt, I have a blue line going to 0, staying at 0. But after that, it starts tracking the peak value of the input voltage. However, does it reach to the green peak? No, it has a difference of about 0.6 volts. V in minus VO is here the drop across the diode, VD. And then when the peak value of the input falls below it, the output remains again at that level because the capacitor holds that voltage level. Remember, C equal to Q over V. And it goes with that. And again, this little bit up, there is this waveform. The output is trying to catch up the peak value and stays there. So every time your output goes up again, the output value is going to that, and after some cycle the output is constant. So it's a kind of filter that we see that we have this half wave rectifier with the regular filtered output. There are the ripples are being minimized, and you have this nearly constant blue line, and that's the magic of your capacitor. Let us plot the voltage drop across diode also. So what I'm going to do, add a plot pane, and I would just print the difference between the V1 and V out. So right click here, add trace, and I will say plot me the difference between V1. So V1 is this net voltage minus V out is this one. So I will just click OK. And here is how your diode is varying from about 0.7 to minus 1.4. Yeah, so there is a peak value variation. That's the voltage across the diode during positive and the negative half cycle. What if we change the direction of this, the value of this capacitor to 10 microfarad? So it has a larger capacity, and we just click OK, and you see we have a better kind of constant output. So you have like the in the first positive half cycle, you have a capacitor, the voltage across capacitor trying to reach the peak value, and thereafter it's nearly constant. So that's how it goes to work. Okay, now the next task is to just cut the nets from here and select this diode and just rotate it by Control R, reverse the direction, and then place the wires again back to their position and see how the behavior of this circuit. Obviously, now it is going to work in a negative half cycles. So run the simulations again and you see it's a negative peak tracker now. The waveform has changed and the forward voltage drop across the diode remains the same. But this is how you can build a simple peak detector using the diode. So hope you found this video useful. Try some experimenting yourself and share with others. Put some comments based on what you think. Like, hit the like button. Don't forget to subscribe and stay tuned for more engaging contents like this on electronics. Till then, wish you happy learning.